do some additional stuff. You're even given some of the wrappers you need to be able to complete Project 4. And you can use our Project 3 solution if you want to. And at this point, I think the teams are probably reasonably stable. I posted information about the final exam, a couple of messages about it. It's from 4 to 7 p.m., fairly late on Wednesday, June 12th. And it covers the entire quarter, again with slightly greater emphasis on the second half, and material for the projects can be covered on the final, although I won't be asking you to write anything in C, C++ on the final. You get to bring in your cheat sheets as usual. I did post last year's final over the Memorial Day weekend on Piazza under resources exams. I've even gotten the first question from somebody about the answer to one of the questions on that final. There is no answer sheet. I don't post answers to the 181 finals, but if people want to ask questions about things on Piazza, I can answer, other students can answer. There's a really good answer to the question that was asked, which is how you make sure when there were forwarding addresses that you don't go to the same record twice, once based on where it's really stored, once based on its forwarding address. The answer that was given was excellent. And I also answered several other questions that I asked you to address in Project 2 there. I had gone over those answers in class, but I hadn't posted anything on Piazza about them. So in my response, I also went over the answers to those other two questions there. So those, I hope, will be clear to everybody. Let's see, plan for the remaining lectures. This is lecture 15, and we'll be finishing up transaction processing, and we may actually finish lecture 15 today. Lecture 16, and this is a change in the order of what I posted in the syllabus. There are two topics I want to make sure we address because they are potentially on the final. One is parallel database and the other is distributed database. And so I'm going to move those up to lectures 16 and 17. And so those will be the next two things that we talk about. Each of them is probably approximately one lecture's worth, maybe a little bit more worth of material. So I should be finished with all of those lectures by next Monday, or actually more likely Wednesday of next week. And then there's material that I had expected to present earlier, but I'm delaying, saying more about log-structured merge trees and write-optimized storage, which I already told you a little bit about. I will try to go through both that and possibly lecture 19, talking about an access structure for spatial data. And it might be stuff that we go about talking about in the lectures, but the material in those lectures, the new material there on LSM trees and spatial data will not be on the final, whereas the parallel DB and distributed DB will be. So it's important to go over that first, and so that's a permutation of what the syllabus described. There are these things called student experience of teaching surveys sets, which are the evaluations. It's a new name for them, which started this year, and they are open and they close the Sunday right before finals week. So please go ahead and do those. Instructors can't identify the individual responses. After a month after they close, we can see the aggregate answers, so it's not something which anybody looks at or can see individual writing or even see the aggregate that's been written until way after course grades are given. And again, constructive responses can help improve future courses. And now we're going to jump back in to discussion, and these are slides we went over, but I'll just remind you about them, about how things work with write-ahead log. And the really important properties of write-ahead log, which give it its name, which is write-ahead log, are that you have to force the log record for any kind of insert, update, or delete, and that must end up making it to disk. That's what the forcing and flushing means, before the corresponding data page gets written to disk. And as we talked about last time, that's important because if you have a data page for a transaction that reflects a change that's been made for that transaction might roll back / abort. And if it does, and you've written a data page that has the change, you have to be able to undo it. So before you can write a data page that has a change that might be undone, you have to make sure that the log record for it gets written first. and that's why it's write-ahead log. The other property is that all the log records that exist for a transaction have to also be forced before the transaction can commit. So you have to make sure that those have made it out there, before the commit record for the transaction. The commit record and having that written out says the transaction really happened, and you can tell a user, an application, that the transaction committed. But the log records on behalf of that transaction have to be out first, because just as you need to make sure that things that are supposed to be undone get undone, you have to make sure that things that are supposed to be done are durable and will be there even if you don't get to write out all of their data pages. So you need to make sure that everything on behalf of the transaction can be redone if there's a commit. So number one allows you to undo if the transaction rolls back, and number two allows you to redo if not all the data pages for the transaction have been written, but there's a failure, and make sure that the things that are committed really do get done. So number one guarantees atomicity, that the undos end up happening on behalf of the transactions that weren't committed. And number two guarantees that, again, it not only guarantees durability, it also guarantees atomicity of the committed transaction. So number two does more than just guarantee atomicity. Number one guarantees atomicity so that things that are supposed to be rolled back really do get rolled back. And number two guarantees that commits are both durable and atomic. All of the commit ends up happening. So we have this ARIES algorithm that we looked at. And again, just very quickly, since we went over this last Friday, there's this notion of an ever-increasing log sequence number that goes on and on and on and on and on. That's written to the log, and the log looks like it has to be infinite, but we'll talk about why it doesn't have to be infinite, which question people ask. We'll talk about that very soon when we get to checkpoints. And the log sequence numbers is a log sequence number for every log record you write. They're always going up. And there are things involving LSN. There are a whole bunch of things that end in the letters LSN that exist that are part of how we make sure that the properties we talked about for write-ahead log end up occurring. So every data page contains something called the page LSN. This is a definition. And it's the LSN of the most recent log record that involves an update to that page. There can be a whole bunch of different transactions that are updating a page. Some of them may have already committed. Some of them may be active and will eventually commit. Some of them may be active and will eventually roll back. Some of them may stay active for a long time. But basically, the page LSN is just one value that is kept for each page, which is the log sequence number of the most recent log record that corresponds to an update to that page. Now, not all log records get forced out. We're talking about operating in a steal no force environment. What does steal mean? As a reminder, steal means that you can sometimes write at a page even though not all the changes on that page have committed. And force would mean that you write out a page every time there's a change, but we're operating in a no force environment where we don't want to force out the data pages every time there's a write. That would be a low performance way of doing things. And so there's this notion of what's called the flushed LSN. And the flushed LSN is the maximum LSN flushed so far. Remember the important property that when you flush part of the log, everything before it must also have already been flushed. And the log is a sequential thing. So when you do the flush, you're going to write out whatever sequence of pages hasn't been written, so far. So if there are 5 pages that haven't been written that are in the log, and you decide you want to force out a particular page in the log, all the pages ahead of it get flushed as well. You can't consider the a log page to be forced out until all the pages before it have been forced out too. You don't leave gaps in the log. Okay. So that's really important. And so we have this term page LSN, the LSN of the most recent log record for an update to a page. And you have this notion of flushed LSN, the maximum LSN that's been flushed so far. And again, LSNs keep increasing, and you never flush an LSN without all the previous stuff being flushed as well. And so the write-ahead log condition, the number one on the write-ahead log thing that we had on the previous page, says that before before a particular page gets written, its page LSN, which again is defined over here, the LSN of the most recent log record for an update to that page, has to be less than or equal to the flushed LSN. Now, there's a degree of freedom as to what the flushed LSN is. You flush more log pages, the flushed LSN goes up. And so before a page gets written, you have to make sure that you flush all the records that correspond to changes that were made on that page, all the log records that correspond to changes on that page. So saying that page LSN is less than or equal to flushed LSN says that all the log records that involve that page have been flushed. Okay? It's the same thing as number 1 over there. We're just saying it using things that are implementable. It's not just a property, it's something which is easy to implement. So you will flush everything in the log to make sure that, log flushed LSN is greater or equal to page LSN. If flushed LSN is already greater or equal to page LSN, don't gotta do any flushing. But if flushed LSN is not greater or equal to page LSN, you do some more flushing to make this true. Okay? A log record, as we talked about last time, basically consists of a bunch of different fields, and there are some special different types of log records that we started going over and we'll spend more time on. The log records form a linked list with all the log records for a particular transaction, so that if you undo that transaction, you can follow that linked list to find all the things you have to undo on behalf of that transaction. So you have prev LSN is the previous LSN for that transaction. Okay, the XID is the transaction ID of the transaction that caused that thing to be written. Every log record is written by one transaction. The type could be an update, which also includes insert and delete. There's no log record written for selects. Okay, and we'll talk about other types in a second. And then there's information where you have, and there are variations of this that can exist using RIDs, but basically you have a description when you're doing this physically and not using the RIDs. You have the page ID, and you have what the heck changed on that page. So you indicate the length and the offset that corresponds to the change, and the before image and the after image. This all assumes you're writing the record in the same place that it was originally. When things move, it gets a little more complicated, but you're not going to go into it, but it's not a hard variation. Okay, so you're basically saying, here's what changed, and here's what it was before, and here's what it is after. As a reminder, when you have an update, you don't write the whole record. The record might be, several thousand bytes, and all you did was update one of the fields of the record, in which case, when it's an update and you're only changing one field, you only have to describe that field, its old value and its new value, because the rest of it is there, whether the change took place or not. So if you need to undo, you only have to change the new, which might be there, back to the old. Remember, changing back to the old is idempotent. If it already had the old value, changing it again changes it to the old. Changing it twice to the old is okay. And also, if the thing was supposed to be committed, then if the old value was there, you write the new value instead. And again, that's idempotent. So that's the case for the update, including the insert and delete. Remember, for insert, there is a new record, you have to write the whole thing, but there's no old one. For delete, there's an old record, but no new one, but you do have to describe that it's a delete. There are also several special types of records. Some of the obvious ones are, you write a commit record. That says this transaction committed. The writing of the commit record is what really does the commit. That says that it happened, it's atomic, it's durable. We'll talk about the property that you need for that, which is that, again, all the log records on behalf of the transaction must be out before the commit record, and the commit record has to be forced, which means all the log records before it get forced, which means you can redo it. You also have a rollback record, which says that the thing didn't, isn't occurring. Okay, and remember that as we're going to come to, when you write a commit record, you're going to have to force it, and therefore all the things before it. For a rollback record, you don't have to force it. The reason you have to do for a commit is when you have a commit, you have an obligation to make sure this darn thing happened. If the rollback record doesn't make it to disk and there's a failure, it'll be an active transaction that existed at the time of the failure, and it'll get rolled back anyway. So you don't have to bother forcing the rollback record. Okay. And the write-ahead log principle is going to allow you to undo any changes that were made that have to be undone. There's an end record that just says all of my obligations with respect to completing the commit or rollback have been taken care of. Don't worry about trying to complete their actions. That's been done. And there's a really weird one as I've mentioned a couple of times now, the hardest part of getting all this stuff right is making sure that things work if you crash during recovery. Okay? It's very easy, in quotes, as work, but it's relatively easy to write a crash recovery protocol that works if you don't have to think about what happens if you crash during crash recovery. The CLRs are there in part for handling things during crash recovery crashes, and we'll see how that works in a second. And this is where we sort of stopped last time. There are things that are maintained in memory and that will have to get recovered in some form after a crash. These are data structures in memory, but again, we'll see about how you recover them after a crash. There's a transaction table, which gives you information about the status of each transaction. So there's one entry for every currently active transaction. Often you're also going to have entries for some committed transactions until you can forget about the committed transaction. But basically, it's going to have information about the transaction ID and its status, which might be running, committed, or rolled back. And for each transaction, it's going to have its last LSN, the last log sequence number that corresponds to that transaction. Which, by the way, if you have a transaction that rolls back, you follow the last LSN and you use that and you undo the last LSN that corresponds to it, and its previous LSN linked list allows you to undo all the actions of that transaction. So last LSN gives you the latest log record that corresponds to the transaction. If it rolls back, you follow the linked list based on previous LSN to undo all the things on behalf of that transaction. Then there's a dirty page table. This has nothing to do with read uncommitted. It talks about pages that have been changed. Remember, back early in the term, we talked about the dirty bit and about the pin count. Pin count helped you know how many people loved that page and wanted it around. Dirty bit indicated whether or not the page had been changed since you read it in. And it's either dirty or it ain't. Being dirty multiple times, it's just dirty. And in the dirty page table, there's going to be one entry for every page in the buffer pool that's dirty that says, this is a dirty, stinking page. It hasn't been written out to disk. And in that dirty page table, you not only have an entry for every dirty page in the buffer pool, but you also have something called the rec LSN, which again is a new character in our play. And that's the LSN of the log record, and this is important, the first, right, the LSN of the log record that first caused the page to be dirty. Could have been dirty for 5 different reasons, but you have the log sequence number of the change that first caused the page to be dirty. Okay. And now, executing a transaction, it's just a bunch of reads and writes followed by a commit or rollback, or possibly an active transaction that never had anything going on with it, and if there's a crash, that active transaction is going to get rolled back. We'll assume that write is atomic to disk. That is, that when you write a write and you're told that it worked, that it ends up working. One of the last things that I mentioned last time is something having to do with the way logs, for example, get mirrored. These days they may be replicated more than 2 times. But here's a game that gets played with respect to log pages, and you have to be kind of careful about it. If I wrote, let's say, I log pages, let's suppose all my pages are 4K, they're usually a lot bigger than that these days, but suppose that I wrote a 2K log page, and I said, okay, this transaction committed, I have the commit record on that page and a whole bunch of other log records. And now I want to write more data on that page because I don't want to keep a lot of gaps in my log pages. I don't want to have too many extra unfilled log pages. And I write that log page again. Now I've filled in an additional 1K, so now there's 3K worth of data there. The trouble is that the way writes work, when I write my 3K page, it might fail and I might have a page that's written out to durable storage, which is garbage. Doesn't happen that often, but it can happen. Now, my not having written the latest 1K isn't a problem. I mean, until I commit that, the transactions in that other 1K are committed. But the 2K that I wiped out had transactions that I needed to keep durable. And by wiping out that log page, I have undurabilized a term that I've just invented. I have undurabilized that transaction, which is not a good thing to do. Like the Duracell bunny, it has to keep on going and going and going and going. Durable transactions should not be wiped out. A game that used to be played, now you do more things with multiple replicas, is you bounce back between mirrored logs. So first of all, you have your logs on different pages, different devices in your disks. Because if the disk fails, if you have a media failure, you have your log and your part of your database together, you're wiped out. Your insurance policy is no good, because it was kept in the same house where your data was, and they both went up in flames. Okay. But here's the way that you bounce back and forth between your logs. You have 2 copies of the log. You write to the first copy. You write that synchronously. You wait until that's completed. If that thing is completed successfully, then you can write to the second copy of the log knowing that the thing's completed successfully. And now you have the second thing, and you're going to bounce back and forth. You want to have something else that gets forced, you're going to write it to the second copy. And if that works successfully, you're okay, and you can see about writing to the original first copy. You're going to bounce back and forth between these 2 different things. And the thing is that you always are going to have 1 copy of what you tried to be able to write. And if one of them ends up failing, you have successfully written up to a given point on the previous one. So again, you have to be very careful about how that ends up working. You will, anytime you say that a transaction has committed, you know for sure that you have at least 1 successfully written copy of the log before you do that. And again, these days it's more likely to work with more than 2 replicas. And you can play games with, working with RAID with this as well. We'll be talking about a strict 2PL environment where, again, it's not just 2PL, which ensures serializability. You can also use 2PL without serializability. But the thing that we want is, to ensure that we don't have cascading rollbacks, and the strictness takes care of that. And again, as I mentioned, we'll be operating with steal, no force, right-ahead logging. And here's something that I had promised last time, and now I'm going to fulfill that promise. The log is all you ever need to recover the database. The database is a very interesting view on the log. It's what you get by rolling forward and applying all your log records. That's all the database is. There's no reason to have the database at all. You can just apply the log from the beginning of time. Of course, databases tend to keep running and running and running and running like that rabbit. And if you have to apply the log going back from 3 years ago to be able to recover the database, that's going to take an awfully long time. So there's no notion of what's called checkpoints, which used to be taken, let's say, every several minutes, and now maybe taken a lot more frequently than that. And the checkpoint will allow you to go back to recover the database using the current state of the database and the information that's in the checkpoint and the information that's in the log after the checkpoint started. And those 3 things together, the state of the database and the information in the checkpoint and the log since the checkpoint started, will allow you to be able to recover the state of the database rather than going back to the beginning of time, which could be a long time ago. Right? Going back to Genesis to restore the database is not a friendly act. Okay, so here's the thing that you do. You write a record when the checkpoint begins. You keep track of what the logical time is. It's on one system, so you keep track of what the time was, when the checkpoint began. Okay, and that also basically can correspond actually to the LSN that you did when you wrote the begin checkpoint record, which you're writing to the log. Then there's an end checkpoint record, which is what you get after you gather all the information that has to go inside the checkpoint. You will write all that information out as part of an end checkpoint record. So it's another special type of thing, and it goes in the log together with all the other stuff that's in the log. So what's inside the checkpoint? Important. While you're taking the checkpoint, while you're gathering all this information that goes inside the checkpoint, transactions are continuing to occur. This would be really easy to do if you said, I'll finish all my current transactions and I'll have a consistent state of the database, and I'll just basically be able to recover at that point. But stopping work while you take a checkpoint, again, is not a friendly act, and we want our databases to be friendly. So this is called a fuzzy checkpoint because you're gathering information that may not be entirely right, but you can use it to recover the state of the database, even though the checkpoint itself may not be 100% right. Again, playing these games with idempotence and so on. So what you're going to do, recall on this previous slide, you have this notion of a transaction table and the dirty page table. That's what you're going to write out in the checkpoint. It's in memory, but you write it out in the checkpoint. But remember, things are changing while you write it, but it's okay. These tables may be changing while you work. This is why it's called a fuzzy checkpoint. You're not stopping work and saying, give me a snapshot of this exact data and write it out and don't do any work. It could be changing, but the changes are not going to be a problem. So everything, right? The tables were accurate at the time that you began the checkpoint, but more things can be happening since you began the checkpoint, okay? And basically, you don't try to force the dirty pages to disk. That would take a long time. But you do write the description of the dirty page table, and you do write the description of the transaction table, which has all the status about transactions and dirty page tables, and LSN that corresponds to the LSN for that page. And so it is a good idea. I mean, basically, if you have too many pages that are hanging out in memory for too long a time without being written out to disk, then there'll be lots of dirty pages in the dirty page table. So, if you've got nothing else to do, flushing pages can be a good thing to do so that you don't have lots of dirty pages hanging around. But there's no obligation to do it. It's just better for performance to flush pages periodically. And now, basically, you have your end checkpoint record. You want to put the LSN of that end checkpoint record, because you need to find it. You want to find the LSN of the most recent checkpoint. You want to put it in a safe place. Now, my wife and I have jokes about safe places. If we put it in a safe place, it usually means we can't find it because it's in such a safe place that we don't remember where we put it. You may have had the same phenomenon in your life. There are places which are called a master record, which again is going to be on a different persistent storage location, not where the log is. Just could even be on where the log is. That part is okay. But you have a particular location, a fixed location, a block on that disk, where you put the master LSN, the LSN of the most recent checkpoint records. Okay, and you're going to keep that in a place where it won't get wiped out. Even when you write it again, you again bounce back and forth with the same game I talked about with bouncing back and forth with the log. So you put that in a safe place so that if there's a crash, you know where to find the end checkpoint record of the most recent successfully completed checkpoint. You know where to find it. And there's a fixed place. Now you may say, fixed places are ugly. No, they're not. They're part of engineering. You want to have a fixed place where you can find something. You want an anchor, so you can find something, so you can get started with a cover. So that's how you do it. So we have these three things that are together, and I describe them as a triangle. And 2 out of 3 are used when nothing goes wrong, and another 2 out of 3 are used when something goes wrong and there's a crash. When you have the information that's in memory, in RAM, and in the database, that's stuff that you're keeping track of while everything's running and things don't crash. You're writing to the log because you want to make sure you can recover if there's a crash. But you don't use a log except as something to write to while normal processing is going on. And in RAM, you have, stuff that you're doing on behalf of executing the transaction. You've got the transaction table, the dirty page table. You have the flushed LSN value, which is a single value. And you have the data that you're doing on behalf of transactions, including the actual pages that are in your buffer pool. Then you've got the database, and that has data pages, each of which has a page LSN that's associated with it, and you have this master record that we talked about with the last checkpoint that's out there. That's out there on disk or the persistent storage. Question?
How do you recover the log if there's a media failure?
This is why there are usually dual logs.
Got it.
First of all, you don't put the log at the same place as the database, and the usual approach is to have dual logs, as I mentioned before, or even more than 2.
Got it.
Okay? So now then there's the log. And the log has all these special kinds of records we talked about, and when it comes to updates, you know, basically it describes the before and after stuff. It's like one of these ads, before and after every record. You've got the stuff, and you've got these write-ahead log principles that we've talked about. And this allows us to be able to use an algorithm such as arrays to be able to recover. So how do you recover if there's a failure? You've got the stuff that's in the database, and you've got the stuff in the log. You don't have memory anymore, but you can recover using the database and the log. And again, you have this master record as an anchor, which helps you be able to get started with what you need to do. Okay, so basically, let's talk about what happens when there is an explicit rollback of a transaction. I've already told you that, but the slide discusses it. So there's no crash here. What you want to do is to, on behalf of the transaction that had to roll back, you want to roll back the transaction. So how do you do it? You have the last LSN, which is the last log record that was written for the transaction, the latest one. There could be more, but the latest one that you wrote. And if you're rolling it back, there won't be others. And you undo it because you've got the undo record, so you just put back the old value. And then the prev LSN gives you a chain of records that you can follow, and you undo all of them. Okay? And here's the thing: before you start to do the undo, you write a rollback record. And the rollback is there, which will, as we'll see, for help recovering from a crash that could occur while you're doing the undo, because you want to make sure that the rollback completes. You may have started the rollback, but you may not have finished it. Okay? So you're going to write a rollback record which says, this transaction isn't sleeping, this transaction is dead, for those of you who are Monty Python fans and know the dead parrot sketch. You really want to undo this transaction, even if there's a crash in the middle of your undoing it. So you just follow the linked list using last LSN and going with the prev LSNs, and you undo all the transactions that are there, all the log records that are there. And basically, to perform the undo, you actually have to lock the data that you're undoing. So as you walk through, you want to have a lock on the data. You know what? That's one of the easiest parts of these. You wrote the data. You've got an exclusive lock on the data anyway. So that's not a problem. That's pretty darn easy. And now, before, and this is the most cockamamie part of this thing, as I've told you, before you restore the old value, you will write a compensation log record. You know what a compensation log record is? It's something that says, I'm undoing this. You write a record that says, I am undoing this. So you continue doing logging while you undo, and you write a compensation record before you go ahead and you do the undo. Now let me emphasize something. What was undone, the undo never gets undone further. Let me say that again. When you have an undo, even if there's a crash while you're in the middle of doing the rollback, do you ever have to undo the undo? No. If you've restored the old value, you've restored the old value. And that's what you were supposed to do. So you don't undo rolling back to the old value. That's going to hang around. Again, this relates to why you need the CLRs. So a CLR record has one special field, which is called the undo next LSN. I read that as undone XT LSN, but it's not. It's the undo next LSN. Should capitalize the N to make that more readable. So the CLR record has an undo next LSN, which is the prev LSN of the thing that you're currently undoing. Remember, there's a linked list of the things you're undoing. So the undo next LSN tells you what's the next thing for this transaction that I have to finish undoing. And that's written into the log record. Okay? And CLRs are never undone. They might be redone, but they're never undone, because the whole point was, I want to undo the effects of this rollback transaction. I don't undo that. I can do it, and again, redo is always idempotent. Doing it twice doesn't hurt. So we're okay. And again, this gives us our atomicity. When we complete the undo successfully, and this transaction has been rolled back, we write an end record, which is really an end of the rollback record. There's going to be an end record for commit, there's an end record for rollback. This is really I took care of the rollback. You don't have to roll it back anymore. You don't have to consider it. It's already been taken care of. And so the end record, once that actually gets forced out, says you don't have to go ahead and do anything on behalf of undoing this transaction. It's been rolled back completely. It's taken care of. There are variations of some different log protocols. What about commit? I'm glad you asked. To do a commit, you write the commit record to the log. I actually threw in a couple of things on the slide. Some of you may download. I have a CODA slide that I've added to this, and I also added a slide telling you about this, the sets and about the chapters that we're going over, and I made a couple of changes on the slide. So letting you know you should download the current version. But so when you write the commit record to the log, all the log records up to the transaction's last LSN have to be flushed. Now, they may have already been flushed, because again, remember the log is shared by lots of different transactions. It's not a separate log for each transaction. The LSNs go, constantly increasing with a whole bunch of different transactions being written to the log. And all the log records up to its last LSN have to end up being flushed, which will guarantee that flushed LSN is greater or equal to the last LSN, which is that second condition which is a condition that I require for write-ahead log, right? For the second condition for write-ahead log, number 2. And again, log flushes are sequential and synchronous. I don't regard the flush as being done until I know that the flush has been completed. Okay? Sometimes people play battery backup games and they say, I know that it will be completed. It hasn't been completed, but I know I've got battery backup and I know that it will happen. And people often are willing to accept that. Notice, however, that since I'm writing a commit record, that commit record has to be after all the LSNs for that transaction. The commit record follows all the log records for the transaction. So if I flush the commit record, that'll take care of all the things that are before. Okay, and that's okay. And remember that there can be many log records on a log page on behalf of many different transactions. And now I'm about to tell you something I briefly mentioned. I'll explain something which is often called group commit, sometimes called boxcarring. I can commit a transaction in 1/5 of a disk write. You're going to say, how do I get fractional disk writes? Now remember, log pages are being written all the time, and when I want to flush a log, I can do one write that flushes the tail of the log, the part of the log that hasn't been out there. So that's basically one command to go ahead and do a flush. I can do the following game, especially when I have blocks in my log that are bigger than 4K. I can't tell a user that his or her transaction is committed until the commit record, and of course all the log records before that has been flushed. I can delay a little while before I flush that block. Don't want to delay too long because people like getting responses that the transaction has been committed. But I can trade off, believe it or not, I can trade off better throughput for slightly longer response time, slightly longer latency. And here's the game. I will wait